please welcome Anat Gilboa to the stage.
So just a clarification, the Cavalier Band doesn't accept violinists, but I am actually classically trained in violin, but that's a separate issue and not actually, didn't try to be part of the band. But go Who's. Hi, I'm Anat. I work at Blue Apron, mainly on their iOS app, and today I'm going to be talking about my quest to understand the relationships between types and categories. So I came out of a conference in October, like many, convinced that I was ready to learn the fundamentals behind functional programming in Swift. I had heard category theory being thrown around in conversation, and kind of felt left out of the conversation because I wanted to understand what this cool hip thing would, and how what it was and how it would help me become a better functional programmer. But the initial intrigue didn't just come out of that conference, though. When Swift initially came out, it didn't really take a moment to step back and really understand what it was about the language that allowed us to use some of the cool, neat features like map, filter, reduce, and I didn't understand why we didn't get that in Objective-C, or what was different about Objective-C. I felt that all I was taking advantage of Swift for was for its nicer syntax. So I felt like I could just learn this branch of mathematics on the side in preparation for this talk by just reading a roughly 500-page book by Bartosz Milewski, aptly named Category Theory for Programmers. I thought that if I had conquered the material in this book, I could just give you all here a crash course in category theory. I kind of jumped into it without a clear reason as to what I was going to get out of learning it, though, and I hadn't realized what it had to do with functional programming. So when it came time for providing a bio for this conference, I gave myself a head start and pretty much forced myself to commit to this topic. I spent hours and hours learning about these abstract ideas in category theory and thought that by the end of the book I'd come away feeling like an enlightened functional programmer. But all in all, category theory is pretty hard. I'm just going to say it was hard for me to learn. But I'm not going to make the goal of this talk to teach you about category theory. The title of this talk has gone through so many iterations, I actually just changed the name like 5 minutes ago. But that leads me to today's agenda. We won't be comparing monads to burritos, though I have linked the popular blog post that started that analogy at the end of these slides. And this isn't going to be a crash course in category theory or type theory or compiler theory either. What you can expect, though, is an overview of what functional Swift might mean for us, what it means for a language to be functional, and we'll go over closures for a bit as well, and talk about the relationship between types and categories. But first, let's talk about Swift. So when Swift came out, folks were pretty excited about the features that it had that made it different from Objective-C. After all, Swift is a general-purpose programming language built using the modern approach to safety, performance, and software design patterns. On the About page, it's described as safe, fast, expressive. And this, for me, was just a fancy new language that we were all excited about for some reason. I was just happy to get rid of those brackets. It's actually pretty cool, though. It's got a bunch of features. But of these listed here, I'm going to talk about closures, and I'm going to talk about functional programming patterns. So, what makes a language functional? Well, actually, according to Wikipedia, just functional programming is a paradigm. It treats the computation as the evaluation of mathematical functions and avoids changing state and mutable data. This is taken from Wikipedia. So I'm just going to just think about using functions to decompose and avoiding state, right? But a paradigm just means a worldview underlying the theories and methodology of a particular scientific subject. So if Swift is actually just a multi-paradigm language, where does that leave us? And why are we interested in this particular paradigm? Turns out that there are a lot of programming paradigms. Just to name a few: procedural, object-oriented, functional, generic. But paradigms just help us decompose big problems into smaller ones. And it's not necessarily bad to use one over another. We can use them together, and they help us. We can use multiple to help us solve the big problems that we're solving day to day. We're used to see, for instance, we're used to seeing things in kind of a procedural way. We're taught to think about things kind of in an object-oriented way, to see the relationships between objects that are self-contained. We can also see the benefit of decomposing problems into smaller parts. But to be honest, I think the main reason people were excited about Swift as this functional programming language was because we could apply these higher order functions to collections and generics. And you may already be familiar with these, but I'll just go through a refresher of map just in case. So you can use map to loop over a collection and apply the same operation to each element in a collection. And here, in the closure, we use shorter syntax within these functions. So we're squaring the values in our array, and we can return with an array, a new array that is each of the values applied with the function. Now, this is all well documented, but all in all, functions are defined for collections in Swift. But say we want to do something more complicated. Well, in Swift, this is actually just a function on a collection, but we can use this closure syntax, which can be a little bit confusing. To be honest, for me, it took a while to get over the general structure and syntax of closures. Even though they look and act a lot like blocks in Objective-C, I would still have to reference this helpful site to recall the different trailing closure syntax and whatnot. But closure is just defined as a self-contained block of functionality that can be passed around and used in code. It can capture and store references to any constants and variables from the context in which they are defined. They allow us to encapsulate logic in one place, and kind of like functions. And they're actually, they just are functions. Swift treats them as first-class citizens, meaning we're allowed to use them as values and pass them around as such, capturing the context in which they're used. So for example, one area that we already use them is this idea in UI View Animation API that we can perform a set of animations in sequence and then respond to the animation's completion. And as we can see in the method signature, we've got a closure escaping from void to void and from Boolean to void. So if we want to call the API, all we know is that within the animation block, we're not actually expecting anything, and we're not actually expected to return anything. But in the completion block, we're expecting a Boolean, so I can check for that completed in, and I can check for that and say, hey, we've completed the animation. Let's take a look at, we actually use closures in a bunch of places. Let's take a look at another example. Some of you may be familiar with the construct of a promise. Well, there are a bunch of implementations of this, but I took a look at our friend Sarush's library for a nice, simple example. In their most basic usage, they wrap data that you want to return and can safely fail if they get an error. One of the primary benefits of using promises is the ability to chain them, and you can use them for asynchronous operations. For example, say we want to fetch some users from our backend and then filter out the ones who are not named Lucy. We call the API, return an array of users, and then we can filter for the ones named Lucy. Now, the actual library itself has easier and nicer ways to use this, but in its most readable way, we're actually using filter in here, and we're just returning an array of users in that first block, and then we can catch as well, so both closures. And then say we want to get Lucy's follower count, the first Lucy's follower count, and make sure that she's got at least one, and then do something with it. And then we can go on and aimlessly, but I'd like to point out the ability to chain these then blocks together. Sometimes we should remember that the compiler is actually trying to help us out, but just by a show of hands, how many times have you ever used the compiler to tell you what type you're expecting? Just raise your hand if you've ever done that. I'm proud of all of you that have not done that. I'm really just so impressed. Well, that's just type checking. And this is the fruit of Swift's rich type system. The compiler has the ability to tell us, hey, give us an error. Hey, we're expecting followers. And here we've actually assigned, we're going to return void. And actually in nicer Swift syntax, you don't have to say the return void. But I'm able to, understand that I'm working with an array of followers. I'm sorry, an array of users. And the compiler is able to prioritize somehow, I'm not a compiler engineer, but it's somehow able to prioritize an ordered list of suggested types or functions upon keystroke input. Which leads me to trying to explore type systems. A language's type system specifies the operations that are valid for which types, whether they're variables, expressions, or functions. They're helpful for catching certain kinds of errors because they have a set of rules. We'll go over the components of compiler design in a bit, but I'd like to point out in the graphic, just looking at these arrows, if you can imagine the types that you're working with, there are properties and there are methods on these types that you can they kind of return some kind of value, and they're all return types as well, or void, which is also a type, but we're going to get there. So they themselves have relationship to themselves, but I haven't illustrated how int can be connected to string, but I'll get to that. So what? Like, you're probably thinking, what does this have to do with category theory, and how did I get here? Well, for the next part of this talk, I'm going to ask you to use your imagination. We're going to talk about types a little bit differently, and in a very, very basic sense. But first, I have to get an assumption out of the way. You all know what a monad is, right? Monad is just a monoid in the category of endofunctors. What's the problem? James Irie's satirical reference to Saunders Maclean's categories for the working mathematician. It's actually, all told, a monad in X is just a monoid in the category of endofunctors of X with the product operation replaced by composition of endofunctors and unit set by the identity endofunctor. Okay, raise your hand if you understand what that says. Cool. So my goal for you at the end of this talk is not for you to feel like you can walk away just bragging to your coworkers that you know what a monad is. After all, it actually took me a bunch of weeks reading the definition over and over and over again, trying to understand, and I think I may have gotten it. But instead, I hope you can walk away with an idea, an expanded idea of how types work and how we can relate them to categories. So let's get started from the fundamentals. A category. Category can be defined as a set of objects and arrows, morphisms between those objects that show a transformation more than a relationship. They have an initial object and a terminal object, and that object may even be the same object. That would be the identity. Now, where does this take us? Arrows can be composed. Basic composition in your math class might look like, say we have these two functions, and we want to increment and then square. When we pass in 2, we can increment 2 to get 3, and then square to get 9. Composition, in essence, allows us to take two functions where the input matches the output, the input of one matches the output of another, then we can get a whole new function. Now, I'm not going to demonstrate this in Swift because there are actually a lot of great videos. I'd point to the guys at Point Free. They've got a good one on function composition. But in math class, you might have seen it like this, more so like substitution. Now, in categories, you just have to define them with two things. For a category that has objects, for any two arrows that are between those objects that are composable, there needs to be associativity and identity. So if you apply from A to B with H and from B to C with G, you need to be able to apply G after H, which is the arrow from A to C. Similarly, G and then F lets you apply from B to C and then from C to D gives you a function from G to D. It's the way that you would think about how an int to a string would allow you to get an int to a string. Generally, when we talk about category theory, each category has a model that you'd like to talk about. So for us, we're talking about objects as types and arrows as functions. And that is the analogy that you can maybe use to compare to this drawing up here. And with identity, an arrow that's composed, that can return itself, is just an integer that can also just a function that can return another integer. Now let's see how this works. Just to recap, objects and arrows, and associativity and identity. Well, a set is, in the broadest sense, a category. And categories can be big and small, but for the purposes of this talk, I'd just like to point out that I'm recognizing that. And in the set of all sets, again, use your imagination here, really just like you can close your eyes and like really think hard, but in the set of all sets, when an object is a set and is like a collection, and the category and the morphism is a function, so mapping one set to another, that's the set of all sets. It contains all of the sets in the world that you can possibly think of. And that forms the large category set. But we won't get too much into the weeds of this. I'm just pointing out that the larger set is a category. A monad is a monoid in the category of endofunctors. So we just said what a category is. Turns out that a monoid is just a type of category. More generally, a monoid is a category with a single object. It's a set that's equipped with a binary operation with similarly multiplication, where you've got the identity and you've got the operation that also satisfy associativity and identity using the left and the right. So just like what we just mentioned, but I didn't say that a category itself had to be a set. It's just a collection of objects and transformations and morphisms. A set, we're defining that it has objects as and this binary operator and transformations as well. And they both satisfy the same axiom that a category does in associativity and identity over this operation. So same thing. We've got associativity, identity, and it's a set. But now we're actually getting to the good stuff, because a monoid by itself isn't actually that exciting. The monoidal category helps us, the monoid within the monoidal category is actually where we get to the good stuff. It just needs to follow some other rules. A monoidal category is a category equipped with some notion of a tensor product, like a bifunctor. For example, the set can be made into a monoidal category with the Cartesian product as the tensor product. Maybe in your math class you remember this as the disjoint union, but first, maybe you just want to understand what a product is. Well, product is just a set of pairs. Say we've defined a type product and A has properties A and B. We're able to project from the product from this type onto another type, A and B respectively, but when we construct, we need to have both A and B in order to construct a product. So it can't be A or B, we've got to have the whole product. Essentially, no optionals here, all of these have to be types that exist. So on this projection, when you create product with hello and 3, you get the projection of A onto A as hello and the projection onto B as 3. Similarly, if you can category, our category, product as the orange circle, applying the projection from A and applying the projection onto B, you have to have, that's the function f and g respectively. In category theory, we talk about introduction and elimination. And if, in its easiest sense, introduction for a product is all of the arrows pointing to the product. So we have to construct using both A and B. And its elimination, well, we don't really care about its elimination right now. But if you think about it, every struct or object that you think about, that you create that has like more than 2 types, or at least one property on it, is a product type, because it could be within the Cartesian product of the 3 or the 4 or the 5 pole, right? The tuple is just the most basic unit of this idea. Similarly, actually, in the opposite way, we have a product. And we can think about them as A and B, but you can't construct one with both. We would think about them as the enum. So you can construct the left product or left coproduct or the right coproduct, but we're not requiring both A and B. And then similarly, you've got a projection from A to the coproduct of B, and then from A to the coproduct of A and B, and then from B to the coproduct of A and B. So its introduction is with the either left or the either right. Combination is the either left or right into C. Some other languages see this as either, but so similarly with the string and int, we can construct them as follows, but we've also got one of these in our language, known as optional. For the purpose of application, I'd like to introduce another type, result. So similarly, it can encapsulate a value or return an error, just error. Actually, it could return type T or U in its most general case, but in this case, we're talking about a return type of error. So let's keep that in mind. But where does this bring us back to the bifunctor? Well, a bifunctor is just a functor whose domain, which is on the left side of the arrow, is the operation of tensor product, which is actually a functor back into the codomain that is just one of those. So if you can see that the types match, so you have one underlying C, kind of like a second order, and it flattens into a first order C, that's the idea of a bifunctor. So a monoidal category is just a category with objects and arrows, and it preserves product and coproduct under associativity. And in essence, it's a category for which every 2 elements you can create a product, and you can create 2 elements, you can create a coproduct, like a sum type. But we've gone over what a monoidal category is, and we've gone over what a monoid and a category are, but a monad is a monoid in the category of endofunctors. Well, let's just talk about functors first. So a functor is just a mapping between categories. It takes one category and embeds the information from that category to all of the objects and arrows in the other one. So it has to apply to the objects and the arrows, and it preserves all of that information. In a broad sense, functor is a moral equivalent of a function between categories. And as we can see here, we can see that with the arrows. And that seems fair, but in order to preserve its functor, it has to stay contained. But I actually just like this definition more. A simple intuition is that a functor represents a container of some sort, along with the ability to apply a function uniformly to every element in the container. You may be familiar with this concept already. A functor is, in essence, a type that implements map. We've got an array, it can contain, and it can apply a function onto another array. An array is the same as an array because they're just containers. But we already know what map is, and you may have seen map works on optionals and arrays, and in our case, result. So for instance, if we have that value that we want to encapsulate, we can map over with our function from T to U and return result of U when unwrapping that function and unwrapping that value and applying the function to the value. If we have an error, then if we can't unwrap that value within our enum, then we return an error. But that's all encapsulated in a result. But I actually, in case this doesn't make sense, I like this illustration of map from Aditya Bhargava. You've got 2 wrapped in an object, you unwrap in a box, you unwrap it, you apply +3 if you can, And then you get 5, you put it back in the box, and then that's contained in the same box. Or if you have nothing in the box, you don't have anything to apply, but you still have a box. So we just defined what a monoid category, what the monoidal category is, and what a functor are, but what is an endofunctor? An endofunctor just maps objects of the category to objects of the same category. Its simplest example is the identity functor, or if you can think of the objects just in its most basic sense, the category, the identity function. And in this case, the function is a functor. So here's where I'm going to ask you to take a quick break. If a bifunctor is a functor that takes you from the product back to itself, so you've got the Cartesian product, then with this binary operator and the domain is the Cartesian product, like the pair type, then it's a monoidal category. But in the model of our category, where we're trying to describe types, functions, types or functions, we really only have one category because we're in the category of types and functions. So everything in here, we have an endofunctor in our category. So for example, we've got map, and we want to extend that. So say if we have a nil value in our first result, and we just want to return a result of result. So this is like a double, application of map. Let's try to implement a function that takes the nested result and flattens it to a simple result. So here we have t, and we're going to try to apply and do the same exact thing that we did with the first map, but just apply it again. But here you can see that the input parameter is result of t, and then we return type result. We're able to do this because we're essentially unwrapping and unwrapping again, then putting it back into the first box, because we already know that result of result can return, that this map can return, that flat map is essentially the bifunctor, which